Yeah, I think that was a great introduction in this topic. I'm with NC State. I started over there about 2 years ago. My background is in human physiology, thermal physiology, and performance of people in extreme environments. And before that, I studied physics, but let's forget about that part. In our TPAC lab, and I'll tell you a little bit of what we do and what we maybe know of, we get a lot of requests on innovative materials and how to evaluate them. And I want to share a little on things we've done in the past to demonstrate performance, and also talk about what we call Compete, our initiative to work together with industry to try to come up with, I prefer to call it a joint, a common language to talk about these concepts and these properties and what they mean and what their consequences are. And that would be our goal, because if we have a common language from fiber all the way up to the end product, if not the consumer even, then it helps in helping everybody explain what it is that a certain technology does and what benefits we would be looking for. So, TPAC, I'm not sure if how many of you are really familiar with that, so I thought I kind of make sort of a transition slide. A lot of people who visit our college, College of Textiles at NC State, you're probably quite familiar with that one. A lot of people visit TPAC actually because of the pyroman and the fire testing we do. All the demos through our great college at some point end up in that pyroman test lab, and that's basically TPAC is associated with that flame and fire testing. And we do a lot of that. It's a very important part of what we do. It's textile protection and comfort center. So chemical protection is one topic. Fire protection is one topic. Chemical protection, which expands these days for firefighters into smoke and similar issues, is another big topic. However, if we would just study these topics, it would be fairly boring. It is not that difficult to protect people against, I wouldn't say anything, but a lot of those things. Just build a lot of layers, a lot of clothing, a big wall, anything. However, the challenge becomes in protection and comfort. The challenge comes in the combination. So through that research that we did for military and firefighters over the last 20 years, we learned more and more about what is the impact on the human body. We learned more about the impacts of heat transfer, moisture transfer, the effects of sweat and how it interacts, and how you can influence that and how you can measure that. So therefore, textile protection and comfort center, that part of comfort center has grown and become more and more strong in everything we do. So although we are mostly known about this side, we're actually very active in this side as well. And we do research, we do testing of clothing, military, firefighters. We do a lot of testing services in terms of comfort. However, we do limited research because usually this is federal government grant money, big projects, long-term projects, and the cycles in industry are much shorter. The budget for this type of more basic topics in industry are also much smaller. So it's difficult to come up with good research projects to address that. So that's basically what our Compete initiative about. I will end with that part. We'll tell a little bit more about projects we did over the last 1 or 2 years that have to do with comfort, moisture management, and topics that are of interest to the AATCC community. At least I thought they might be interesting. So yes, besides all that protective clothing, all that protective research we do, we basically, and these are, I try to not select a protective clothing in this case, but even our protective clothing research projects always end up with something like this. We want to know what the materials do, but in the end we want to evaluate the impact to the human. How long can people work in it? What happens if it gets warmer or colder, and how do people respond, and how can we change that? But even from the comfort research, the starting point will always be the material. On one side, how does it transport moisture? We'll look into that. And the other side, how does it the hand and feel? Everybody working in clothing and textile industry talks and wants to know, and basically first responder and even fabrics, basically how does it feel? And we try to put numbers to that aspect as well. So if we look at comfort, and I'll explain more of those concepts, it's not just about liquid, sweat and moisture management, not just how hot you get, it is also about hand and feel. It's a very important topic in the overall comfort research. And I'll try to show a little, I'll try to keep it a little bit short today, which is challenging for me. So I'll try to address each of these topics. So the question we asked ourselves is this one. Can instruments predict comfort response? Because yes, I tell you, we go all the way in our research project to a human evaluation, yet we do know, and we would be the first to acknowledge that a human trust wear trial is expensive, is elaborate, is time consuming, and is complex and complicated in terms of good data analysis. It is very difficult to get good scientific reliable results from it. It is possible, yet let's say challenging to do so. So anything we can do before that, basically what we try to do is design our whole range of experiments and whole set of experiments in such a way that our human trial in the end does not give us a lot of surprises anymore. We actually know what to expect and what to look for and what the data will roughly tell us. It sounds like that I'm already writing a conclusion when I haven't done the experiments yet. That's not what I mean. We try to think about how to set up the conditions, how to set up the protocol, how to really look at the properties that are of interest to us, because we measure that with instruments. So this is our real challenge. Can we make those instruments? Can they give us the data that allow us to predict what we should be seeing in a human trial, and then test if we indeed see that? Usually we do, sometimes we don't. It's still research. So if we look at testing levels, we have basically 3, maybe 4 levels, depending how you count. You start always at the fabric test. And mind you, and I probably don't need to tell, I left that graph out here. If you go down, the level of complexity increases, the level of cost increases, and the level of time increases, of course. However, also the level of realism increases. So that's where your trade-off is. So you want to start out with all your fabrics and materials and variations that you can get to screen out and see how they respond to know, and then down select to the next level in which you start fabrics, garment systems. You make the fabrics into a garment. So we do most of our work in clothing, although we do a couple of other products as well. I've come up with a generic term for that. Human interactive products or something like that. And then we make them in clothing and we measure them on our instrument and mannequins first. It's kind of a good transition before going to human data, because it's still reliable and reproducible and accurate and consistent, but it's more complex already, because now we have a 3-dimensional system instead of just a flat 2-dimensional fabric. Then we move to controlled human wear trials, which is in our climatic chamber. We know the environment, we know exactly what people do. We can, I wouldn't say measure whatever we want, but we can measure a lot on humans. And the final level is field evaluations. Notoriously uncontrolled if you're not careful, and can be very realistic, of course, because it's in the field. It should be very close to how people actually use it. So in the end, that is where you want to get some of the information as well. And let's say it's a trade-off between accuracy and effort. This is highly accurate, highly repeatable. Standardized test methods typically do this because of that reason. It's accurate and repeatable and reproducible. So if we look at comfort, I mentioned to you, one thing a lot of people look at is heat and moisture vapor transport. This has to do with the thermal physiological properties. How warm do we get or how cold do we get if the environment changes or the environment is challenging, let's say. The other very important aspect is sensorial. Mechanical surface property, that is the hand and feel. Sounds very scientific to say hand, mechanical surface property, it is the hand and feel, which is very important to everybody who's wearing clothing. And again, this is where heat and mass transfer and sensorial impact interact. The liquid moisture management, to a large extent, very strongly influences that hand and feel. In some cases, we suspect, if we talk about wicking, and we're going to talk about a little bit more, this might be even more important than that. That is something to keep in mind. But there's, in terms of comfort, it's even a little bit more complex. Probably that's a good thing, because that's why there's a lot of discovery, and there's a lot of exciting things to discover. Obviously, we talk about physical properties, we talk about temperature, we talk about moisture, humidity, pressure, mechanical interaction, forces. That's maybe that physics background of me that does come handy after all. We talk about the interaction, what all that does through the human body with its human physiology. So obviously that is important. We know if we get hot, we sweat, we get cold, we shiver, and we have all kinds of responses in between. However, psychology is also expressed as a condition of the mind, which is actually a very intriguing topic if you want to think about it. There's very little research on that. All the research that is in there basically is fully on the marketing side. But if you think about it, this is the physical, physiological interaction is usually how it's put, is one dimension. The psychology of it is the other dimension. There are people in literature who describe comfort as the absence of discomfort. To some extent that is true, but it just merely is that you're on one axis only. It just means that if I remove all discomfort properties, I remove all sensations of heat and cold, I remove all sensations of prickliness or pressure or pain or whatever, that is the highest that is comfortable. There is, however, good literature in terms of comfort on the psychology side of it, which tells you you can actually influence that people are even able to accept some level of discomfort while still be very appreciative and comfortable in your product. And that's usually the area of what marketing people do. That's what they try to do. And the best example that I got from a colleague who's an expert in anthropometry, he basically did for the military, tried to fit people in cabins of trucks and then also cars. And he was telling me, if you look at the average sports car of about $100,000 and up, those seats are really not comfortable. The suspension of those cars is really not comfortable. If you think about ergonomics, and he's an ergonomics scientist, so he's an expert on that. However, people are very comfortable if they drive those cars. Ferrari, Maserati. That is something that is limitedly explored in clothing, I think. It is also, probably if you think about branding, Apple, maybe what some of the brands do has some of that aspect as well. So that is another scale of comfort. I have to admit, we specialize mostly in this. I have had some intriguing discussions with colleagues from the psychology department on this within our university and outside. So there may be room for doing more in that area, but we haven't explored it really yet. So, those first two topics, physics and physiology. This is kind of what we know. We don't need to really explain it. If we get hot, we sweat. There is a lot of unknown in sweat. There's a lot of literature on sweat. There's a lot of questions on how is the sweat distributed over the body. There's some nice papers on that. There's some knowledge on that. When it gets warm, we sweat. So that means while we work or are active, we will sweat. Or if we are not working and the environment is very warm, obviously. It's the same thing. If our body gets hot, we start to sweat. Sweat is a very efficient cooling mechanism, so if we evaporate our sweat, we cool ourselves. There is really not a better cooling mechanism than that, even if you look into the chemistry and physics of it. And therefore the sweat must evaporate to cool us. That is a topic we'll get into. Yep. Another interesting aspect of the skin, and I thought a little about if I should put it in there, and just briefly, I won't go into full detail over this. The most interesting thing here is actually here. If you look at the sensors and the nerves, the sensory system of the skin, you have basically you have temperature sensors separately for cold and warm, which will give a sensation from the skin to the brain, I'm feeling warm or I'm feeling cold. If it gets too warm, you'll see pain start to arise. If it gets too cold, you also see pain. Both are very painful, I can tell you from experiments. This obviously is a burn, and this under cold, being prolonged at skin temperature here, we've done experiments in the past on that, it's very painful. Pressure, obviously, we feel things, we rub things, strain. In terms of our whole liquid moisture management topic, there's one thing missing here. We do not feel moisture. We do not have sensors in our skin to feel moisture. However, I don't think anybody here maybe do, so please challenge me, I would love that. We do feel when our skin is wet, I would say. So how do we do that?
Is that just because of the cold?
It's a combination, yes, actually. It's a combination of a cold sensation and a tactile, usually cling sensation. If you have both, you can actually make people believe that the clothing is wet. Usually, it does require looking at it. So there are some very nicely developed experiments which people have indeed blindly made things cold and sticky, and they were able, and I've had experience it myself on a cool spring day where I was sitting and my leg was cool and I was not looking at it, and it's like, hey, it feels like it's wet. It was just that there was shade there and it was much cooler than the rest. So it's a difference, a temperature difference, and a tactile sensation that is integrated as feeling wet. That's a very interesting aspect of the body mask. Well, if we look at moisture management, I'm not even going to try to put up here how many tests there are, because it would not fit, or it would be so small that you wouldn't see it. There's a lot, you're probably even familiar with tests that I probably don't even know. There's a lot out there, and every test does different things. So they might actually all be useful depending on what you're looking at. I'm taking water. So, some of the important ones, gravimetric absorption is one that measures how fabrics pick up water and how they spread it and then evaporate. Moisture vapor transmission is a very simple and old test which just looks how vapor passes through. It's a very limited and quick screening test. Vertical wicking is a very simple thing. You put a horizontal wicking right there. It just measures how liquid transports. It's liquid moisture transport. Sweating guarded hot plate, it's about heat transfer, but it's also about water vapor transfer. In a standardized way, you have foil there which limits or prevents liquid contact of the fabric to that hot plate. Whereas if you go to the, well, you can actually there should be a mannequin here because we try to adapt it as well. If you go to the sweating mannequin, you have a combination of vapor and liquid contact, so you suddenly see the interaction. And the list basically from there goes on and on. If you go to the MMT, the moisture management tester, it is a liquid spread of a limited amount. Just as an example, to put one in, and if you do the GATS, you have a liquid pickup of a fabric, and here you see different types, and you see basically a different temperature. This was at 35 and this was at 20, so you see temperature effect, and you seem to see some effect here of a treatment. What is it? So actually absorption was higher because this is actually grams and this is time. Neutralized it, anonymized it a little bit too much maybe here. So this is your maximum absorption capacity, and from this point on, your fabric is naturally from itself maximally absorbed, and there basically it starts to, the reservoir keeps losing water because it evaporates from the surface. So basically the two effects combined. So that's a nice way. What we do challenge with the standardized test method here requires you to do interpolations here and find a reflection point here. Sometimes it's difficult to find difference in fabrics that you can see in the graph. So sometimes looking at the graph gives you more information than the standardized data that come out. Don't go over the numbers. If we look at those similar fabrics in this case, the only thing I basically want to show you here, they're very, and these are insulation values, there are very little difference here. Basically, if you look at this test method, typically if differences are below 5%, it's a non-significant difference. So any difference you see here, it's the only thing I wanted to say here, they're non-significant. Yeah? So we pick it up on the gas test, we see differences there, we don't see no sweating guarded hot plate. And that's only vapor transfer. The sweating mannequin also did not pick it up. I didn't want to bore you with more details and more tables and more numbers. It gave you a very similar picture. However, we have an infrared camera because a lot of people who come to us want us to take infrared pictures of their newest technologies, fabrics and fibers, because of this reason. The color is nice, even on a nice early Wednesday morning, everybody, I mean, if you have to, most people would prefer this above this, I would say. Yeah, right? So that's why it's used. Our mannequin measures heat loss. It did not measure differences between the two, so the control and the treated. However, you can see something interesting here. This is at 20 degrees, this is at 35. You see, this is warmer. And you see what you see here is basically the liquid front. What happens is that mannequin has contact to the surface. The surface the mannequin produces water. It has a very thin wicking clothing that basically wets out the entire surface. So there's liquid contact here between the mannequin surface, say, and the clothing. So it picks up that water and it starts wicking it to some extent, and that's what you see here. This is the liquid front because there is no contact here. It's hanging on the surface here. So you see actually that in the treated fabrics, especially there and there, it actually wicked faster in the same amount. I don't remember, I think it was about after 10 minutes or so, 5 or 10 minutes. The reason you don't pick it up on the heat loss is twofold. One, you measure a wetness difference here, which is the clothing and not the mannequin, so it is probably limited because you're cooling clothing and not the mannequin surface. The second thing is we have two segments, we have a segment here and a segment there. So basically our cutoff between the segments right there. That's another reason it's very difficult to pick it up because it's right at the edge of both. So it's, the sensitivity, the measurement sensitivity is not big enough in this specific case to pick it up. So this was one of the few occasions, I would say, where infrared pictures actually did say more than numbers. And we are usually trying to avoid it because it's very difficult to come up with good numbers to try to describe this and to quantify this. An IR camera can give you beautiful pictures. The interpretation of it is not always easy. In many cases, it is complicated. Here you can say this was cooler than this, basically. There is so much. Yeah. And then we ran actually a lot. We ran most of the tests I just showed you in the first graph, and we had an external test report as well. I tried to anonymize that as well. You might recognize it. I don't know. This is actually a type of hot plate, but it's different in setup. And you see different fabrics here. And basically what happens here is where sweat starts to produce. Here it's dry, and you increase, and you start adding sweat to the system, and therefore it cools down, because in this setup, the amount of heat flowing to the surface is the same. That's why it cools down, similar to a humid body. And you see a small difference there. That's basically, so that's where we see a difference, similar to what we saw against. Here is basically where the sweat stops. There was some, this is probably more, there were some differences there. It's probably more the regulation of the whole system itself than it is actually from the fabrics. This is another version of it. It's actually from the torso, so I really should be knowing where this comes from. And this is the weight. So this basically, it start dry, you add water to the system, and then basically you let it dry again. So you stop your sweat production here again. Here again, you see some differences here. So these were, and if you do the analysis, these differences are very similar to the differences we've seen in the gas test and other different, I pulled them out. And differences we saw on a small plate where we were able to add limited amounts of sweat to this system. And I'll show you that. But you can see that, yes, we can measure those differences. We can measure it here and there. We could measure it on the gas test. In the end, the question is still how relevant are these differences for the human body? This already suggests some answer to that question, but not entirely. The thing we can say, it is a transient effect. It's temporarily there. It is there when you start sweating, when you have an initial sweat production, so not your full garment is saturated, because as soon as everything's saturated, basically, there is a fixed amount. That's actually more. You can kind of see it, it kind of all comes together, because you just have a wet clothing layer outside of your body at that evaporates. That's all that's going on. Yeah. With our mannequin, this is the reason I put it in, so we measured in a standard way. What we do have these days is the possibility to connect it to a physiological model. So what we can do, it deviates from a standard test with very reproducible results, but we can predict better what happens when the average human basically would wear that system and be out to any climate that we provide. And we can run the model itself, we can also run it in a climatic chamber with our mannequin, measuring that specific clothing system, and then we're just bound by the range of our climatic chamber. So we can do everything. Yes, so I did skip the other ones because of time. Good thing. And tactile properties, I promise you some of that as well, because like we saw, so we see that a lot of those moisture properties are transient in nature. We can measure them, we can quantify them, but it will be only in that period when we're just outside the comfort range, which is for a longer time just outside that range, or for a short time when we really get warm, when we start producing sweat, at those first 5 to 10 minutes. So you can look at it in terms of usually a comfort range and how you change that range of comfort from one fabric to another. It's not absolute. Comfort is always relative to the environment. There's always going to be, for every clothing system, a lot of conditions where you're uncomfortable. So, feel and touch. Haptics is the study of sense, touch, pressure, and texture. This is our, I would say, famous Kawabata system. So what it tries to do is take some of those measurements and measure and put numbers to it. Measure that roughness, measure that friction, measure the bending, which is basically it's a two-dimensional thing because it's a fabric, but it basically bends in one direction only. Shear is very important for drape characteristics, which is a 3D characteristic, it's a two-dimensional bend. Pull it, and then you start to change the shape. There are very limited capabilities for drape testing these days. Bending, there are multiple options. It's not only our bending test that we have. The drape is difficult to capture. I know in visualization software, people are working on that to try to do a better job on that because it's important how things look as well. Surface roughness and friction. Tensile, but it's different from your standard tensile. In standard tensile strength is basically how strong it gets into the drapes. This is really in the subcritical range. You see how it behaves in that much lower range, everyday wear basically. And T-Max is that equivalent to initial sensation if I reach a fabric, how is it perceived basically. What a company, SDL Atlas, has come up with a FTT tester, which does most of it. It does the tensile, the bending, and the surface roughness and friction. It does not do the shear test. And currently we're evaluating how that system performs to our range of equipment. And I think, well, so this, and obviously the compression thickness tester is there as well. So it's bending, it's shear, so you can see the ribs here because you pull first and then you start to wiggle it a little bit. And then the shear. The challenge is, what we see from it, it works quite well. The thing is, mostly it is a black box. So if we put fabrics in there, we get numbers. But if we put fabrics through our Kawabata system, we have to mount them manually. And our people are expert. Well, the people who do it are expert in it. Because before we let students do it, we train them. So we really know what's going on. If we get a curve that has some kind of funny characteristics, we redo it. Because we see what's going on. It's not that we get a number as an output. And that helps us as experts, if I may say, to understand how a fabric behaves and really see what's going on. However, it is very elaborate, it's very time consuming. So I can see where the FTT tester, being a black box, would be very useful, for example, for quality control. You want to just basically have a repeatable test that is fast out there. I just put it on there, and I know if I do the same fabric every time, basically I can't compare with it. There are some issues there that we haven't really been able to match what the FTT tester found to what our Kawabata test found, even on the same test. We're working with the company on that actually. But beyond that, we know the effort response. Usually we evaluate our Kawabata system to a hand panel for a certain product, because hand and feel is related to the specifics of the product. So it depends on a lot of things. What we also haven't really looked at much is how things will change over time, or with different groups, different populations, for example. There's a lot of questions in that area as well. Yes, so what we always do is if we have a certain fabric or a new fabric, and we haven't done it before for that product category, we evaluate our results from the Kawabata system with a hand panel. Because we expect different things from our t-shirts than our jeans. And that's where the psychology comes in again. It's the expectation. Because the expectation is different, the scoring method will be different as well. And That is a very relevant aspect of the whole hand and feel sensation. But it's still knowing all that. If you do a hand panel the right way, and we do use the AATCC test method for that. That's the basics. You can really come up with good, controlled, standardized results that are repeatable. So the kind of questions that we are stuck with basically is are all these results between tests consistent? Can we compare vertical wicking versus horizontal wicking versus MMT versus gaps versus I'm out of breath? All those other ones. Yeah? And if we measure differences like we saw, what do those differences actually mean? How relevant are they? And even to that question, the answer is not always the same. Because it can be relevant to have small differences in some conditions. And then from fabric to the mannequin, and can we compare the mannequin to the human data, what differences are there? And we can see, and basically, it's all about this question in the end. What differences can we perceive? And we are not there yet. We know to some extent, even in heat loss, how much difference in total heat loss for a human body is actually relevant. Is it 10 or 15 watts per square meter or 20? Or we are close to an answer there, but even there we're not. And that should be the simplest actually. And that big question on how does wicking actually influence cooling? Is it possible to have a wicking fabric that actually cools you? And I would love to have a big discussion on the language issue we have there. What does cooling actually mean? And what does a cooling fabric mean? How would we define it before it cools you? Or is it just that it doesn't really hinder your natural cooling that you already had? I'm open to the discussion at the time. So what we try to do, and I try to give you a brief overview, is to basically, because we do all those tests, we get loads of questions. We work with industry. A lot of our testing is non-standard because we want to tweak it to find really the specific technology and how it performs. But it would be great if we can get around those questions, if we are able to get people together to answer at least the question. We know we will not be able to have people collaborate on their intellectual property of their fibers and their finishes. That is fine. But what we can talk about is, okay, so what do we define as cooling, for example? When do we say wicking cools? When do we say this wicking is very good? So what are basically industry standards for that? Can we agree on what measurements we should use to define that? And how should we test it? Should we test? A lot of standardized test methods are stable. What I showed you from the other test institutes and results that we did ourselves is transient conditions, changes in environment, with and without sweat, heating up, cooling down, getting more and less moisture in there. And those test methods can be developed so everybody can use them and at least be on par on what they do with it, what their fabric, how their fabric performs on it, and how we interpret those results. And that is what our Compete initiative is about, trying to get those people together to talk about that. The reason for that is because we get all those similar questions. We would really love to address them, and we know it is expensive to do so. So joining forces for that would really help everybody. What is comfort? What is moisture? What is realistic testing? Because we can test and find differences, but does that make any sense, basically? And I think two things actually. How can we explain quality to our customers? That might be someone buying it, but it might be also if you're a fiber producer, it is the person after your customer who makes the fabric. But it's along the chain, I should probably say. And you can also use these tests to your supplier, basically. It should improve the communication if you talk about the same thing. You know what these tests do and what they mean. And actually, at this point, we've talked about it a little bit before, but we will be starting off. We will have a kickoff meeting by the end of this month. We have 8 companies at this moment who have expressed intention to join, to pay the fee, and to participate in the research to address these questions. They vary from fiber to fabric to brands, basically. They brand. AATCC, that's one of the reasons I'm here today, because we talk to them, we try to work very closely together, because we want to set industry standards for comfort and comfort testing, evaluation. It means that We as NCC can come up with something, but we try to strive for something that is actually useful to industry and can be adopted to industry. So we really prefer to work through and with AATCC on that. And really in this field of testing and evaluation and what is called collaborative research is an option. It's what we call pre-competitive research. It is really talk to a lot of companies and yes, there will at some point be issues, but we can talk about not specific what your product is, but how it performs. That's all we will talk about. Couple topics: dynamic moisture management. How do all these tests and that's the 1 and 2. I apologize for that. Clothing movement and ventilation, because usually we're not standing still in the lab, but we're outside. Modeling and prediction, which is a little bit more complicated than individual difference, and those psychological aspects. At some point I would like to move on to. That's about it. So work with our capabilities and what we do, and I think that's at this point it. So thank you for your attention. If you have questions, it's 8:45, so there's no time for questions. And I'll be here a little longer, and you can reach me on email. I prefer email personally. But you can call me as well, or just try to find me. Thank you for listening.